Okay, so on to the next presentation, and I'm very pleased to be able to welcome Georg Conrads, who is CEO of Promecon, who will be talking about digital gas flow management. Hans, if you'd like to load up your slides now. Having studied electrical engineering and completed his master's degree, Hans founded Promecon and went on to invent numerous measurement systems for the power, cement, and smelter industries. Today, these measurement systems are installed in hundreds of plants around the world. Hans is also the author of numerous patents and many conference papers on process measurement of gas and solid material flows. He's managing director of Promecon, which is based in Balben in Germany. Over to you, Hans.
Well, thank you very much. I hope you can hear me well and you can see my presentation well.
Yes, thank you.
Okay, then I would like to start with a couple of remarks. We have seen two very interesting presentations and I enjoyed both of them very much. And there's two things I want to say. Before we started the session today, we were sitting together and talking about AI and what to do with AI and whether we should maybe have our portfolio managed in the bank with AI. And that was the question, can you manage the future if you don't know it? A very interesting question. And the second thing that came to mind was in one of the presentations, the question was, is it good to add more sensors? Well, again, here, what you can only manage what you see, and you can only manage what you know about. So the sensing is basically one half and the AI is the other half to make sense of the data. So I'm going to talk about how to provide the data. And in the cement industry, of course, there are, like in any process, there are areas where the data is ultimately important and is very, very vital. And then there's other areas where you may add another vibration sensor that is nice to have, but not really fundamental. I'm going to talk about gas flow measurement, and the gas flow in cement plants is a very challenging parameter to measure. We've been working on this since 2000, and I think it is one of the most beneficial parameters that you can have. And whenever we measure that, we can see that cement plants are incorporating our measurement into their expert systems in order to optimize the process. But now these expert systems have become predictive systems, and now they're becoming prescriptive systems. So I think that the use of data in intelligent modeling of processes is very, very essential. And I'm going to talk about why I think digital measurement is so important here. So let me just start off with a couple of things. Just a few words about Promecon. Not all of you may know us. We have been around since 1995. Our main areas are about measuring hot and dusty process gas flows in cement industry, metal industry, power stations. So really, thermal processes is our business, and especially measuring hot gas flows. I'm going to talk about our airflow system today, which is basically a gas flow meter, measurement principle, how to install it, the advantages, and especially also why it is so important that we are digital and not analog. And then I'm going to give you some examples of the cement plant process where we have optimized. And these have been very often optimized with process engineers, hands-on. But it's needless to say that you can use our data in any model and in any more complex control algorithm to optimize the plant. So I think it's really a yin-yang controls and measurement. So as I mentioned, we have been around for quite some time, and we have left quite a footprint also in these industries, including the cement industry. What we do is measure gas flows, but what comes with it is also the analysis of the process itself. And I'm going to give you some examples of that throughout this presentation. The core thing that I want to talk about today is how to measure a gas flow of dusty gas. And this may seem a bit boring because gas flow measurement has been around forever. There have been delta pressure measurements or Venturis or other devices. We've seen thermal anemometers. We have seen ultrasonic, so all sorts of devices. But the main issue here is that measuring a gas flow that might be 1,000 degrees Celsius hot, that might be dusty, that might be very aggressive, that is something that is very difficult. And especially in cement plants, like in other processes, power and steel, the most important thing is that the measurement is repeatable and it gives you the same answer over a long time. If you have signals that are starting to jump back and forth, you are getting process noise, and even with artificial intelligence and neural networks, it's very hard to model that. We've been part of a lot of optimization projects, and the most vital thing that artificial intelligence makes artificial intelligence helpful is the same thing with the operator. If I have repeatability, then I can make of the data a very good process optimization. I have a very nice convergence of my data to find the optimum set point. And we are not measuring in so many places, but we are measuring in some places that are very, very essential. And I'm going to talk about that in a second. Now, the first question is, how do we measure? If we don't measure with delta P, if we don't measure with ultrasonics, or we don't measure with thermal anemometer, how do we measure, and why is our measurement digital? Well, the first thing you can already see, our measurement is always consisting out of two sensors. So we have an upstream and a downstream sensor. And what we are actually doing is fairly simple. We are having two sensors that are sensing the electricity or the electrostatic signal coming from the clinker dust or the raw meal or whatever particles go through the pipe. And what we can sense here is that when the sensors pass by the antenna, they leave a typical time signature, which is basically the change in electric field in the vicinity of our sensor. If you do that on an upstream and a downstream sensor that are spaced very closely, like 300 millimeters, you can see that this pattern is very similar. Yeah, you can see with your own eyes, the upstream and the downstream patterns look pretty much the same. And this is because the measurement, the flow dynamics from one sensor to the other do not change instantaneously. It takes some time for them to change. So if you are within a certain short distance, you can see that this information is more or less kept the same. The only thing you can see, it's time shifted because you're not at the same location. And this way it becomes digital. What you do is you digitize these two signals, and you don't care about their magnitude. You don't care about their amplitude. The only thing that you care about is their statistical match. So you digitize them, you put them into a cross-correlation filter, and out you get the cross-correlation function. The cross-correlation function is basically showing you a maximum at the time shift where the two curves have the best statistical match. So you basically shift them on top of each other and you move them. And wherever they match best, you have this maximum in your cross-correlation function. Now, why is this so important? It is so important because the only thing that matters in your measurement is the similarity of the two curves of the two raw signals, which you then calculate statistically. And that means that the only parameter that you are depending on is time. That's it. So it's a pure time measurement. So if you have a time clock on your processor card, you have a repeatability of 10 to minus 6 or 10 to minus 7. And that's your repeatability. You will not find any measurement that starts to drift over time. And that means that in some central areas of your cement making process, you can establish a certain reference that will not move. There are many other things that move around. And as you both of the speakers ahead of me mentioned, the degree of complexity in these processes can be quite large. And when these processes drift over a long time, it's going to be very hard to follow if all the parameters start to drift and all the sensors start to drift. You will start modeling the inaccuracy of the sensor. Now, with a digital sensor, you will have the same response all the time, and that gives you a huge advantage in converging to the best process quality. So in this case here, that means 52 milliseconds is the time shift. And with the distance of the sensor and the time shift, you can calculate the gas velocity. And using the temperature, you can then calculate the gas flow, including the gas enthalpy flow. So this is how the box looks like. You have two sensors, you have our electronics, and out comes a 4 to 20 milliamp signal, or a digital signal if that's preferred, that gives you the gas flow. What I mentioned also is that we can measure temperature of the gas at the same time. So it's easy to measure the gas enthalpy flow and also the energy flow, the thermal energy flow of the gas. So basically what we have here is a flow measurement that can measure up to temperatures of 1000 degrees Celsius, that can measure in a velocity range of 3 to 100 meters per second, completely linear. We have a huge turndown ratio because we do not have any squared relationships that you might have with delta P systems. With a very high accuracy over the full span, and needless to say, an outstanding repeatability. And that's really what has been our recipe in the cement industry, to have such a high repeatability of our signals and such a low maintenance requirement. A reaction time of smaller than 1 second. And of course, integrated thermocouple if necessary in order to accomplish the temperature measurement. We also have an SIL version of this, but this is not so interesting for cement. Many power stations use that because of the safety aspect of boiler safety. So also power stations are using our system to optimize their combustion. So here's in a nutshell, what is in essence, the main advantage of the digital measurement. We have no K factors that have to be implemented, no calibration, no drift. There's also no big duct modification necessary. We do not shine through the duct, or we do not have to mount sensors on opposite sides of the duct. No regular cleaning or maintenance. And again, drift calibration free because it's completely digital. Now, this opened up the complete world of being able to measure gas flows in locations where they could not be measured before. So imagine you have a vertical roller mill. You want to know how much gas comes out of my roller mill. Yeah, that's different from how much gas do I get at another point. Can I measure right in the dirty gas flow? How much gas is going back to my roller mill or to my raw mill through the recirculation duct? Yeah, what is the main gas flow coming through the downcomer? Yeah, how do I know how much gas I pull out of the downcomer? This is the classical optimization task for optimizing ID fans. How do you optimize your ID fan? Yeah, you have O2 value, or you have some other indication that is not very up to date and is fluctuating around. What if you have, in addition, the real flow value that comes from your downcomer? It's very, very easy to optimize an ID fan. Whether you do that with a classical controller or you integrate it into your overall AI model, it doesn't matter. You have a stable measurement point. Same applies for the bypass or for the tertiary air duct. So let me spend a few minutes of what we have been optimizing as examples in cement plants. I must also agree with the two speakers ahead of me that cement making is very complex. And in many cement plants, there's a lot of attention on predictive maintenance, on repairing things. Optimizing process is very, very sticky, because if you start to optimize on one end, you have many other things that you influence, and you have to keep track of many, many variables. So therefore, cement plants, really, many of them do not have the full potential of optimization that they should have. And the way to go there, I think, is smarter controls along with better measurement in the critical areas of the plant. So let's go through a couple of examples that we have. I will touch upon some of the highlights that we've been seeing throughout the years, what customers have asked for. One of the biggest one is raw mill. Everybody knows the raw mill is a very large machine. It has a huge power consumption. Overdrafting the raw mill has consequences in power consumption, but also in grinding quality, in wear. So nobody wants to overdraft the raw mill. On the other hand, having a flow through the raw mill that's too low can trip the mill, which is something that is even less desirable. So people would like to know, what is my gas flow through the mill? Do I have the right gas flow? And every mill manufacturer specifies a certain gas flow, but it's hard to maintain. So the ID fan has to be operated so that the airflow that is designed, that the mill design gives you, is achieved. Now, this also, of course, has to do with moisture that's in your gas, with additional components that might also be gaseous. So you really have to know the velocity of your gas flow independent from the fan operation. Usually operators like to adjust the gas flow a little bit on the high end. And that is exactly because they want to be sure that the mill empties out, that you don't get a drowning mill. These mills have 200, 300 tons per hour. So if a mill like that trips, it's a monster problem. Now, this safety factor costs you a lot of electricity. Of course, everybody knows that. If you have an ID fan, even if it's a frequency controlled, you have a ratio between flow and electric power of third order. So if you increase the flow just slightly, you need far more electric power. So it's a very big desire to reduce the flow to the lowest possible set point. And for that, you need to be sure of what the flow is, right? If you don't know that, you can try to model it, you can try to find intelligent solutions for it, but usually the shortest way is to have this parameter as a direct measurement that can go into your optimizing system. Yeah. So an example that we have is typically for a mill is 1 kilowatt hour per ton of grinding material. Now, if you have, for example, a large mill, you could have continuous savings of about 150 kilowatt hours for 150 tons per hour mill. Of course, now when I say the ROI is reached after 1,500 hours, that means that, of course, that includes the optimization of the flow. In some plants, it's very simple. People don't have to use smart systems for that. But this is just one aspect. There's so many more aspects in the plant that you can optimize once you know this value. And once you can rely on this value, right? So that's one of the very typical ones that we get. Another one that's very popular is the downcomer. Why is the downcomer so important? Of course, the downcomer carries all the gas that comes from the pyro string. So all the gas that comes out of the kiln, the rotary kiln, all the gas that comes out of the pre-calciner, goes through the preheater tower and then finally comes on the downcomer. And it ends in an ID fan. So you have basically two places where you have ID fans on either side of the pyro process. And if you would like to stabilize this process and you would like to be sure that the amount of gas pulled through the kiln and also pulled through the TAD is as flatlined with as little process noise as possible, the only way to do that is to measure it. And many clients are quite shocked when they see how much the fluctuation in downcomer gas flow is. Now, measuring it is the easiest way to have a good indication of how to stabilize downcomer flow. Also here, I mean, it will stabilize O2 values in the kiln, as it was already mentioned today. All these parameters interact with each other. So making the operation of these very big fans more flatlined and with less process noise will give you an immediate advantage in your controls. So again here, using the ID fan for a fast and repeatable, using the Mecon air measurement for a repeatable ID fan controls will bring you a big advantage in the stabilization of your process. And this has to do with everything. It's fuel, it's stability of the process. It even comes down to a stability of free line. Again, an example here. I don't have to mention that. If you have these large energy intensive processes, if you can optimize them, if you can prove that you can optimize it, you will always make money in a short time. Measurement is a cheap investment. I've heard from my speakers before me, the optimization AI is a fairly cheap investment, besides all the big capex that a cement plant has. So it's really a low-hanging fruit to go for good instrumentation in conjunction with good controls. I give more examples. It is important for many people to know bypass. They want to know how much bypass gas they have, especially in front of their pre-calciner. A very big thing that we have is TAD. I saw there's quite a few people from India in this presentation. I know that in India, it's a huge thing with NOx. If you have a pre-calciner, you blow in fuel. It can be petcoke, it can be coal, it can be fluff. And then you have the TAD, which gives you your combustion air. So how do you know that the fuel to air ratio is correct? You have to measure the fuel, and you have to measure also the tertiary air. So tertiary air measurement has a direct impact on your emissions and on your NOx formation. So how do you measure tertiary air? Right? Until Promecon came along, there was no effective tertiary air measurement. Today we have many, many references throughout the world in tertiary air measurement. Another thing would be waste heat recovery or the clinker cooler outlet. If you want to make a nice gas flow balance on the clinker cooler, you could use that directly to control the fans in and out of the clinker cooler in order to stabilize the neutral point in the clinker cooler and make your clinker cooling more effective. So gas flow, I mean, if you just look at this picture, you can see that gas flow, besides all the, let's say, heavy metal stuff, is one of the most important parameters to measure. Yeah. Last but not least here, gas flow to heat recovery boilers. There are a lot of heat recovery boilers around that become important. The total gas flow management in your plant is really depending on knowing what your gas flow is. So we have been introducing this solution into the market. We have more than 100 customers in the world. We have 192 installations. We have nearly 900 sensors now in 60 countries. So this is not a new solution. I must say we've had quite a few installations where clients have asked us, if we know this now, what can we do with it? I think the first speakers of today are a very good hint to what you can do with these signals in order to optimize your process. I think the perspective to have cement plants optimized have never been as good as they are today. There's lots of good technologies around. And now also, if you want to know what is the most popular, what are the most popular applications, well, we did 46 downcomers, 58 mills, 36 TADs, 49 cement mills. This is compared to what you have as cement plants in the world, a small number. We're just starting in the world market, but still it's quite a big number. And this is where we have installed these systems. I guess there are little areas in the world where we have not been doing some work. Of course, Africa has been very interesting for us. I saw there's people from Dangote, but also, of course, Asia, Europe, US, South America. So we've been pretty much all around the world. And with this, I would like to close my session today. Digital airflow measurement or gas flow measurement is, I think, one of the most important things to come along with good and smart controls to save energy and optimize product. Thank you very much.
Thank you very much, Hans. That's a great presentation, lots of good information, and a really nice fit with the first two presentations. Like you said, it's the old adage, rubbish in, rubbish out. So if you're wanting to make a good analysis, you need to have the right data, you need to have the quality data, and you've provided a really versatile solution there. So thank you very much for presenting that. There's one or two questions. One is, how do you account for the turbulence in the duct and non-laminar flow? So just sort of asking about the working principle of your technology.
Right. Turbulence is basically not a problem. If you, in fact, it's a good thing. If you have a high velocity in the duct and you have a turbulent flow profile, it tends to be more flat. It's not a laminar flow profile where you have, different flow velocities from in to out. But with the typical velocities that we see, about 15 to 30 or 40 meters per second, you just tend to have a flat profile. The only challenge is that you may have a stratification. If you come out of a bend and then directly after the bend you measure, you might have a stratified flow profile. So you have a higher speed on the outside radius and on the inside radius. Now, I must say, especially in cement plants, this tends not to be our biggest issue because we have very long and very straight runs. In power stations, this is far more challenging. And in these power stations, we usually seek to have some sort of shallow section of a venturi or some sort of airfoil where the flow profile, again, is very flat. So I think we can cope with that very well.
Fantastic. And you mentioned waste heat recovery as well. Is that an important application? And is that a growing area of interest for you?
Well, it is a growing area when people want to do mass energy balances. So with waste heat recovery, usually you have a steam or a water side and you have a gas side. And again, if you have intelligent systems and you can do a mass energy balance two ways, the gas path and the steam path, then any mismatch can automatically trigger something in. You can, for example, calculate the cleanliness of your heat exchanger. So there's lots of benefits if you have, if we say in Germany, an over-defined systems. Yeah, you say you need two variables to define a systems. If you have 4 or 6 and it all matches on top of each other, you know that you are correct. Yeah, but if you and therefore, yeah, heat recovery systems are a growing area of interest because there are more heat recovery systems around.
Sure. Well, that's fantastic. Well, thank you very much, Hans Conrads from Promecon, for that presentation.